In this video, we will review your chemistry content, what you have learned in sophomore year. Let's talk about the matter, like a cloud, and the cloud contains water vapor and water droplets too. The water vapor is the gas stage and the droplets are the liquid stage of the water. Water is made out of hydrogen and oxygen atoms, H2O, made out of two hydrogen element from the hydrogen element and one oxygen element. The compounds have fixed ratio of the elements. Water is not the same as H2O2, that is a hydrogen peroxide. I crossed that over because it is dangerous for the body and toxic. The water is the only material on Earth that contains three stages of matter. Ice if it's below freezing point, like 0, and liquid is when it's higher temperature, and gas vapor turns when it reaches its boiling point. Matter is everything that contains mass as well as volume. The body is made up of elements, the human body and all organisms. The elements we can distinguish between among the different elements. The majority of the elements are the oxygen, carbon, hydrogen, and nitrogen. 96% of the body is made up of that 4 elements. The calcium, phosphate, potassium, sulfur, sodium, chlorine, and magnesium makes up 3.7% of the body. And we have the trace elements that they make up the less than 0.01% of the body weight. Focus on more a little bit on the trace elements that make up 0.01% of the body weight or less. They are the zinc, copper, fluorine, iodine, iron, as well as manganese. Let's focus on the fluorine. This element is important to prevent tooth decay, and the cavity will form if there's a low level of fluorine in the water, so they add to the toothpaste as well as to water for people to prevent tooth decay. Iodine is the next element, a hormone in the thyroid gland. The thyroid this is the trachea, the windpipe, and in front of it at your neck area is the thyroid gland that needs the iodine to produce its hormone. If there's no iodine in the food or there's no iodine intake, goiter will happen. That's swelling up at the neck area. To prevent that, now in the United States and most of the countries, you can buy salt that is iodized, so it contains iodine. Unfortunately, 30% of household worldwide lack of iodine salt. So that's really kind of sad, because for infants and during pregnancy, iodine is really important. If the infant or the fetus does not receive enough iodine, mental retardation or mental retardation will happen. The iron, important for the red blood cells, that they contain a hemoglobin, a type of a protein inside of them that carries the oxygen all around in the body, and iron is one of the main components of hemoglobin in the blood. We have focused on the elements now, so let's focus on the atomic structure of the atoms. We have the middle part, the nucleus of the atom, and electron cloud surrounds the nucleus. Definitely this is not to scale drawing. In the nucleus, we have the protons, the positively charged protons, and neutrons that they do not have charges. In the electron cloud that surrounds the nucleus are the electrons. The analogy for that kind of the sun and the planets, as well as the Indianapolis 500 race, the nucleus is inside and the electrons are going all around. Let's go with an example. Iodine-127. These are the two ways we can write it down. This bottom part that I squared up, the 53 is the atomic number, and the top number, the bigger number, is the mass number of the element. Atomic number represents the number of protons in an atom, and the mass number is number of neutrons as well as the number of protons. In this case, in the iodine-127, we see that the 53 will go to the number of protons because it doesn't have any charge, this iodine, so the number of electrons are the same as the number of protons. And the neutrons, we can figure out the mass number minus the atomic number. About the isotopes, that's our next topic. Iso means same in the isotopes, and they behave identically in the chemical reaction with the other atoms. Example for that is the carbon-12 versus the carbon-14. The carbon-12 is a stable element, an atom that it contains 6 protons, 6 neutrons, and 6 electrons. 99% in the environment we can find carbon-12, but the carbon-14 is in less percent, its occurrence, and it's everything is kind of the same with the carbon-12, but the neutron number, it's a little bit more, and it's not stable. The nucleus decays as it turns into a more stable element. As well as it turns into more stable element, it emits particles, alpha or beta particles, as well as energy. The energy that emits can break chemical bonds, as well as because it breaks chemical bonds, it damages cells' molecular structure. So in here, this is a chemical and breaks the bonds. Why did we learn about the isotopes? What is the use of the isotopes? Isotope is really important to date fossils. Like a dinosaur, as a living organisms, they incorporate carbon-12 as well as carbon-14 into their body through eating. The carbon-14 the carbon-14 decays, and its half-life is 5,730 years or 40 years. That's half-life. So finding the percent of the carbon-14 in the fossil is really basically the point to find out the age of the fossils, because when the organism dies, after the organism does not incorporate carbon-14, just only happens when it was alive. This is the way we use the isotopes to date the fossil's age. As we said that for the isotopes, the differences in the nucleus, let's examine the function of the electrons in an atom. Let's take the hydrogen atom, and here is the nucleus that contains 1 proton. The hydrogen, this is how we would write 1 and 1, and the atomic number and atomic mass, number of neutrons, in this special case, hydrogen does not have a neutron. There's an isotope when they do have, but now we consider the majority of the hydrogen atoms. The blue represents the electron cloud that surrounds the nucleus, and we are drawing I have drawn the first electron shell, the S shell basically, that can contain up to 2 electrons. Now, the one electron that the hydrogen atom has, it's on that electron shell. Let's check the helium. The helium is the second element. It contains 2 protons because of its atomic number is 2. Because of its 2, it has 2 electrons as well as 2 neutrons. Inside of the nucleus, we have the protons as well as the neutrons, and in the electron cloud, we have only the first electron shell that will contain really contain 2 electrons. Its electron shell with these 2 electrons are totally filled, so we call it stable. That's why it's a noble gas. It's not going to react. It's valence shell. It's totally filled, so it's happy. Now, check the carbon with its atomic number is 6 and mass number is 12. The number of neutrons, protons, electrons, we can figure out. In this case, in these 2 helium and carbon case, both the neutrons and the protons are the same number, but that's not always the case. I want you guys to keep in your mind that it can be different. In these special cases, they are the same, but not always. Like the iodine, they would have different as we go higher in atomic number. Now, the electron cloud is bigger in here because we have 6 electrons instead of 2. So the first electron shell, the S shell, is going to be totally filled with 2 electrons, and the second electron shell is going to have 6 minus 2 is 4 electrons. The outermost shell is called the valence shell, and the electrons on the valence shell is the valence electrons. Now, the maximum number on the second shell can be 8 electrons, and this is not filled electron shell. So the carbon is unhappy. Basically, it's not having a stable outer electron shell. The valence electrons are really important because they do the game with the in the chemical reactions. Because atoms do not have stable or filled electron shells, therefore they form bonds. The bonds, these are the nucleus, this is the nucleus and the valence electrons all around. Now, we distinguish between a covalent bond and ionic bond. A covalent bond, during covalent bond, the atoms share electrons. They form molecules. If atoms form covalent bonds, we call them molecules. Here is one bond between the hydrogen atoms, and this is a single bond. The methane is CH4, and the carbon forms 4 bonds, 4 single bonds. On the other hand, if we check the oxygen molecule, the O2, they form 2 bonds, and these 2 bonds are double bonds. They need to form bond to be more stable. The bonds, depending on how fairly they share the electron pairs, we distinguish between apolar, evenly shared electron pairs, and unevenly shared electron pairs. Evenly is the apolar bond, happens between oxygen, hydrogen, and methane. Unevenly shared electron pairs happens happens with water. Depends on the electronegativity of the atoms that they make up the molecule. As we go down on the periodic table through the row, the electronegativity hogging the electrons are more prominent, as well as we go higher towards a smaller nucleus, they are strongly hog the electrons in the covalent bond. Water is a great example for polar covalent bond. Ionic bond happens when one of the elements give off and the other one atom accepts electrons in order to stabilize their electron shell. For example, the classic example for ionic bond is the sodium chloride or the salt, the table salt. And for the sodium, it has one valence electron, and it want to get rid of it to have a stable electron shell. On the other hand, the chlorine needs one electron to stabilize its outermost electron shell. So the sodium turns into positive ion as it gives off its extra electron, and the chlorine picks up one electron and turns negative ion. It's a very strong bond, but can be dissolved in water. And most drugs are usually come in the ionic form in salt. As a grand finale, after talking about the electrons and bonds, let's talk about chemical reactions. Chemical reactions, we will use the glucose C6H12O6 and reacts with oxygen to form water and carbon dioxide. On the left side of the equation, the glucose and the oxygen, we call them as reactants. And on the right side of the equation, the water and carbon dioxides are called products. The atoms are identical in the reactants and products, but the molecular formula is different. We have now let's balance the equation with six carbons on the right side. We have to have 6 on the left side, as well as the number of oxygens and hydrogens on the product side, as well as in the reactant side, got to be the same. This is cellular respiration that takes place in the mitochondria in the organisms. Photosynthesis. This will be our other equation that we are going to talk about. So chemical reactions, rearranging the molecules. We break old bonds and forming new bonds. That's really the point of chemical reactions. Only valence electrons are playing over there. No change in the nucleus of the atoms. So photosynthesis, carbon dioxide comes from the outside of the air, binds with water that comes from the soil through the xylem in the stem, and we need energy for this synthesis reaction, and the energy comes from the sun. The end product will be glucose as well as oxygen. Oxygen as a waste. Think about that, plants produce oxygen as a waste. Along here we have to balance the equation because number of the atoms, both in the reactant size and product size, got to be the same.